Morning. Today we're going to continue working on examples, chapter 9. We're going to the initial value problems. So last time, if you remember, we started working one of the problems, the in-class problems that are uploaded on Canvas. We started a problem where we had to do an exact solution integration. It was one differential equation, first degree, and we solved that for analytical. We get the analytical solution, and we were to do the calculation through the Euler method, and also the RK2 method, and also the RK4 method, and I'm going to add also the Heun method as well. So I'm going to write a program for this. So let me share this screen. So if you remember, this is the problem. Let's read that one. So the problem states that, okay, this is the equation. This is the differential equation. It's a first order differential equation. And remember, this is the exact solution that we got last time. So we were to do that, plot it against Euler method, midpoint method, and I'm going to also do the Heun method as well. Okay, and we're going to see which one is really the most accurate one, which is, we know already, the fourth order RK4 is the most accurate one, but we just have to test that, and we're going to test it with these H increment 0.5, 0.25, and we're going to do, and we'll see how they all going to converge when we decrease the this increment. So let's go and start writing our program. And so, all right. So this is we're going to start with, first, we're going to start with H equal 0.5. This is the increment. We're going to do a T final. What is it? T final 2. It's between 0 to 2. So T final is 2. T1. I'm going to use an array this time, index, when I do the for loop. It'll be easier for us when we plotting, when we start plotting, and you'll see the difference. So T1 is equal to 0. That is the initial difference from 0 to 2. So and that's the final. And then you have the initial y0 equal to, if you go here, y0 equal to 1. So y0 in this case is the first index, so it's y1 equal to 1. That is the initial value for the function y. And I'm going to define that f function, which is the dy dt. So dy dt is equal to, I'm going to do the handle function at, and it is t and y. And the function is y times t square, so don't forget the dot, minus 1.1 times t. Okay, and let me suppress that. All right, so this is the dy dt function. This is what we have. And the second thing I want to do, I want to, let me do an array of t. So t is equal to T1, right? This is where we start. And the increment is going to be H. And the final, T final will be, but remember, because we're going to run this plus H plus A, we're going to actually final minus H. And there is a reason why we're doing this, just a minute, because once we do that, start plotting, you'll see that the length of t will be working perfectly, because we are going to add h as we go every time, and the last value will be adding h. This is where we're going to get the t final. So now let's do the for loop. So for, and I'm going to do this with an index. So for I equal to 1 to the length of t. Okay, so length of t. Okay. So this is when we're running I. We're going to do K1. We're going to start with the Euler method. Okay. And then we'll do we're going to plot Euler, and we're going to plot the this equation, the exact solution that we get, which is e to the power t cubed over 3 minus 1.1 t. So let us do the Euler function. So K1, we know the Euler function, we're going to take the slope at the first point, which is I, so at ti and yi. So again, if you go back to the equation, you will see that I'm just gonna go back to Euler. So you'll see here, this is what Euler here, we're taking the slope at ti and yi. Okay, that is exactly, and the slope is dy dt, which is the one that we just entered right here. All right, so that is the Euler method, is taking the slope at the original point, which is ti and yi. So that's going to be equal to f ti and y of I. Okay, let's close that. And so that is key one. K1. So yeah, that's correct. And now what we want to do, we're going to do y I plus 1. We're going to equate it to equal y of I, yi, the original one, I, and plus k1 times h, so h times k1. Okay, so let's suppress that, we don't want to see those. And then we're going to do ti plus 1, that's equal to ti plus h. Okay, that is what I'm talking about right here. Ti plus h right there. Okay, so let's go back in here. All right, so that is this is the loop. So ti, so we're done with that. Let's just end it then. Let me suppress this, suppress and end here. So that is done. And I'm gonna do F2 before I start plotting. I'm gonna call F2, which is the F2 will be the exact solution that we just solved for. It's equal to exponential of t e to the power 3 divided by 3 minus 1.1 times t. And that should give you the exact equation. And let's plot first the exact solution before we plot the. So I'm going to just do t f2, and I'm going to do this with a square marker, so we know distinguish that. And I'm going to just hold on that because I want to add to that all these plots. Let me save that first. Save as. Let's just do P 25 1. Okay, so problem 25 1. Save that. All right. Let's hope that I didn't make any mistake. So let's run it. All right, let's see what we got in here. Basically nothing. So let's what is it that I did not do right? Oh. TF2. All right, so yeah, when we run this, something is not right, and it's because of that array here. If you look at T, you know, every time you just have to be careful. You want to use the colon, not the semicolon. So that's my array, and then let me run this and see what we got here. So you know what? Let me do this. So I'm just gonna do this in here. So look at this. This is the exact solution, and remember we only have a 1, 2, 3, 4, 5 points to plot. So we're gonna actually increase the number of points later on, but this is just to see this is the exact solution. Now let us plot the Euler solution. So we did that. So we hold on this. So let's just do CLC here, and let's plot here T, and I'm going to do Y, but I'm going to do if I just do, let's just do TY in there, and you'll see that you're going to have a let's try that, and let's do this with this marker C. Let's see if we can plot that. So we're going to plot this, and let's run here. So it's going to tell you vectors must be the same length. So it looks like T and Y, they're not the same length, which is one is going to be +1 than the other. So what I'm going to do, I'm just going to make sure that Y it has the same length as T. So I'm just going to do 1, and the array is going to be from 1 to the length of T. Okay, so that's what I'm going to do. I'm just going to run plot. So make sure they have the same vector so we can plot that. And let's run that now. Okay, so let's see what we got here. Something is not right. Hold on, let me just do this. And all right. So I'm just looking here. It's not supposed to be like this off, because if you run this, you will see that this is really off. So something is not right with the equations. So I went back and I checked this here. If you look at here, that differential equation, I am actually, instead of putting y here, I put a t. So that is my mistake. So if I rerun it now, you will see that this is what we get. Now, again, this is the blue one, square one will be the exact solution, and this one will be the red line will be the Euler equation. And just before we move to the second methods, so let me move this here. And if I because he said to do this for 0.25, so if I do this 0.25 and rerun it again, H. So let's rerun that. You will see that always you have to you'll see that this is coming closer to the exact solution. You see the red one. And if let's move it to 0.1 or 0.05, let's just do 0.05 and hit run, you will see that it is almost coinciding with the exact solution. If you do this 0.01 and hit run, you'll see that now we have pretty much similar plot as the exact solution. So yeah, let's keep it at 0.5 now because I wanted to compare it to the other ones. And let's run it here. So let's keep it this way. Again, the bluish square markers will be the figure, and the other one will be the Euler. So now what we want to do, we want to move to the let's do the RK2 method, right? So we'll do the RK2 method. So let us hold on this, and I am actually just do hold on because I want to do this, and I'm going to actually copy back this one and modify it a little bit. So let me copy this, and I'm just going to modify it. Here. And paste here. So what I'm doing here, so this is TF2, we hold on. Then we did this. So what I want to do here, let me just put hold on again, because I want to use the RK2 method. I'm doing everything the same, nothing has changed yet. But I'm going to change the K1, those slopes, because in the RK2 method, we are actually going to get the slope at the midpoint between I and I plus 1. So K1 is not changing for that one. So let's leave that one like it is. But we're going to do K2. So K2 here, I'm going to do K2 here. And K2 will be the slope at the midpoint. So it's going to be F Ti plus H2, right? H over 2, sorry, H over 2, because it's in the middle, at the midpoint. And we're going to have Y of I, and a plus K1, you know, the slope, K1 times H over 2. Okay? And let's close that one. And then here, nothing is going to change except that now we're going to multiply the slope here by K2, not K1, because we want the slope at the midpoint. Okay? So K2 represents the slope at the midpoint, and we're just going to multiply it by H, and let's see if this will give us better solution. So let's go down here. This is going to, nothing going to change. All we did, we just changed the slope in there. And let me do the plot here. And let me just copy these. Copy. It might be very lengthy program, but it doesn't matter. There's a lot of things that. So we're gonna do this one here, and I'm gonna change this to what do you want to do? Do different marker than this one. So let's do this one with a star, maybe. Let's do the star. So we have a square and also one star. This is another star, and so yeah, I think that should do it here. So let's run this. Let's run this one here. So now, if you look at this, remember the one in the bottom is, I'm gonna do legends for all of them. You know what? Let me do that right now. So, and then we'll change that later because we're gonna add 2 more. So just to distinguish between these two. So let me do that. Let's just do legend here. Legend, and I'm going to do exact solution first. Solution, and we're going to do Euler, and we're going to do RK2, right? RK2. And let me close that one so that we can distinguish between this. Let me rerun this one here. So if you look at the legend, let me enlarge this one here. You will see that, okay, the bluish one with the square is the exact solution, and the Euler, you'll see that Euler is down there, and you have the RK2 right here. So definitely the midpoint or the RK2 method is way better, even with the small with a small number of points, like 4 or 5 points, it's still giving you something very close. And if you choose to let's choose to change H for let me do this here. Let me change H and see where we get. If we change H to 0.1 here and hit run, you will see that this one always. So let me do this here. Every time, if you let me bring this one here, you will see that when you I mean, it's not going to give you a good representation because I'm going to change the H for all of them. But look how smooth it is, because it's going to actually, if I change the H for all of them, let's change H for all of them, not just this one. So we're going to change H here, 0.1. I'm just saying, trying to see where, how this is going to affect us, H.1. All right, so let's run it. And let's see here what we have. So you'll see here that if you look at Euler, still a little bit off, but if you look at RK2 and the exact solution, you'll see that we are right there, almost even with 0.1. So pretty accurate method. So all right, we're gonna go back and we're gonna leave this one now, and we're gonna go back and change it to 0.5 because we want to compare, like I said, the other methods. So that is 0.5. We're not changing that. All right, and let us now do Heun method. So far we did the exact solution. We did Euler, we did RK2. We're going to do Heun, and we're going to do the RK4. So now we are going to go back to this one here. So we're going to do, hold on, and let me also, you know what, let me do this here. I'm going to also do yeah, I'm going to copy these here and also paste them here because I'm going to modify a little bit. Now, Heun is a little bit different because let me add Heun here because we're going to also plot Heun as well. So Heun is a little bit different than RK2 because Heun, what we're going to do, we're going to get the slope at I and the slope at I plus H, or I plus 1, and then we're going to get the average of that. So we'll go back to this one here. We'll have K2, we'll change that K2 to, we're not doing this at H over 2, we're going to do it at H. So we're going to pick that half from there. So that is K2. And yi plus 1 is going to be actually equal here 0.5, the average of K1 plus K2. So that is K1 plus K2. All right, so let's put the parentheses in there. And that should do it. That's K1 and K2. So this is the slope at I, and this is the slope at I plus 1. And we are going to average these two slopes. And that's why we multiplied by 0.5 and added to yi, and that will give you the new I plus 1. And we're going to plot the same thing. We're not changing anything, and we're just going to hit run in here. So if you do this, let's enlarge this one here. Before I do this, I want to change this one a little bit. Yeah, let me do this. Let me get out from there. I hope I did not lose it. No, actually I did. Yeah, let me. Yeah. So I'm going to actually change the legend, the marker on there. So this way we distinguish between the plots. So if you look here, we're Heun, we're having the same plot as this. So we're going to change that, even though it has the same color. So that's this one here. And so let's get out from there. And I'm just going to do here a plus. So we're going to get a plus marker in there. And let's hit run. So that's, and let me enlarge this one here. So this is exactly what you're going to say. You will see that the RK2 right there, it's also, look at the blue one and look at the RK2. The RK2 is great. It's very close to, it's similar as, sorry, Heun is actually also close as RK2. So pretty much they have the same accuracy between Heun and RK2, the midpoint. Okay, so far we have the 3 plots in there, plus 3 methods, plus the exact method. So now, finally, we're going to do the RK4, and the RK4, let's do this here. Let's get out from here, and also what I'm going to do, I'm going to hold on here. Hold on. And what I'm going to do, I'm going to copy also, do the same thing here. Copy. And I'm going to add a couple of lines for RK4, because remember, RK4 has K1 through K4 in it. So we're going to add 2 more lines. So we're going to come back to this. So K1, K2. So K4, K3. So K2 here, K1 will stay the same. K2, we're going to add 0.5h right there. Ti plus 0.5 times h. And we're going to do here, same thing here, 0.5, because we're doing this at the midpoint. So that is K2, and times K1, so that's not changing. Now we are going to, let me copy this here, copy, and paste. We're going to paste and change, do some modification here. So now we have K3 here, and here we're still doing it in the midpoint, but now we're going to multiply this by K2, not K1. So if you look back at the equation, just show you here, for you'll see here, that's exactly what it is. K1, this is K2 at the half point, but again, You see this is times K1, this is times K2, and the last one is FTI plus H and YI plus K3 times H. So we're gonna do the same thing here. So let's minimize that, and let us also paste this one again and do some changes here. So this is K4. We're gonna get rid of the 0.5 because we're doing it at the end of the increment, and we're gonna get rid of this one here. We don't need to multiply, it's not at the point, but and also we're gonna do this one as K3. Okay, so FDI plus H, and again YI K3 times H. So that is it. And at the end here, we're gonna do, it's 1/6, remember? YI plus 1 is equal YI plus 1/6 K1. You have the weighted 2K2, 2K3, and plus K4 times H. So that's what we're gonna do. So we're gonna change this to 1/6. Okay, so that's, and then we're gonna do K1 plus 2K2 plus 2 times K3 plus K4, and that's why we divide this by 6, because we have 6 Ks in there, 1 and 2 and 2 and 1, and then we're done. So we're gonna go down here and we're gonna change this. Let's do this one in X marker, and I'm gonna add here the legend. I'm gonna do RK4. Okay, so and let us plot it. Let's see what we got. So here we go. We have RK4 is right there with the X. If you and if it actually coincide with pretty much with the let me move this here, the legend. If you look at the exact solution and the RK4, they're really pretty much same. Look at this, very similar. So Euler will be the least accurate one, and then Heun and RK2 will be very close, and RK4, as you can see, it is just with 4 points, and look how accurate it is. If you were to let's do this here. If you were to minimize the number of or the value of the increment, let's do this one here, 0.1. Okay, let's do it all the H 0.1. And there was a reason why I'm doing this separately, because again, this is 0.1 and this is 0.1. So if you do this and try to plot it, you will see that, you will see that you have only the Euler, it still needs a less increment, but the rest, they're pretty much the same as the exact solution. You see how they coincide? And especially the RK4, it is exactly as the other as the exact solution. Now, if you also if you bring it down a little bit more, 0.01, let's do 0.01 for all of them, and you will see that what is that here? You will see that they all will coincide now, because even Euler will work also just fine. So let's run this here one more time, and you'll see here that look at that. They all pretty much coincide with the exact solution, right? So less is the increment, the better is the accuracy. So this is a great example where you have, again, you have the exact solution, Euler, RK2, Heun, and RK4 solution. So I'm hoping that you guys are doing this as we working. I'm working. I want you to do the same thing I'm doing. Don't just rely on me doing the work. I want you to do it as well. So yeah, this is pretty much it. I'm just gonna save that for this problem. It's a great problem because it shows you the accuracy of each method, and you see the strength of RK4. That's why it is widely used, and the ODE 45, it's based on the RK4 command. So let's move to the second problem, and then we'll stop afterwards. And we'll next session we'll start working on the second chapter 10. So let's go back to here and let's see what we have left. So let's see here. Let's close this one here. Saving that. So go back. All right, so one more problem on this. All right, so let's read this one here. So if water is drained from a vertical cylindrical tank by opening a valve at the base, the water will flow fast when the tank is full and slow down as it continues to drain. It turns out that the rate at which the water level drops is dy dt is equal to minus k square root of y. And this is a fluid mechanics problem. We call that problem. It's an unsteady problem. When you drain a tank, it all depends on the height of that or level of water. And that's why the change dy dt is also a function of y, where k is constant depending on the shape of the hull and the cross-sectional area of the tank and drain hole. And the depth of the water, y, is measured in meter and the time t in minutes. If k is equal to 0.06, determine how long it takes the tank to drain if the fluid level is initially at 3 meters. Solve by applying Euler equation and writing a computer program or using Excel. I'm not going to use the Excel, and I'm just going to use the Euler, and so we'll let's do that. See here. So we'll start a new program. So start a new script, and that is, we're going to start with dt. Step is 0.5, so we're going to use dt is equal to 0.5. And let's suppress that. T initially was at 0, so we're going to start at t equals 0. And then we, y originally, the level of water, let me just do this, level of water originally at 3 meters. So that is also, these are all initial conditions. That's why we call initial value problem. And we're going to start with I equal 1. And let's do while. Let's do this one 1. We use the while loop because this is where you know, what we want to determine how long it's going to drain. When the water level y is negative, once y starts going negative, that means y is less than 0, which is impossible. This is where we know that the tank has been drained. So y is equal to y plus dy, which is the change dy dt. Yeah, y would be equal to y plus dy dt, and we're going to actually do the function dy dt in just a minute, but dy dt, okay, and dy plus dt. Okay, so that is plus dt. So dy dt times dy plus d times dt. Sorry, dy times dt. So what I'm doing here is Euler method says that y is equal to y plus the slope times dt, the change in time. And let me, we'll have to, I mean, I can just do dy dt, but I'm just going to do function, and this way we'll call it in a minute. So we'll do it a little bit differently. If y is negative, and that's what we do not want, we're going to break. And so break and okay. So it's going to keep looping until y is negative, and then in this case t is equal to t plus dt, and I is equal to I plus 1. And let me end this loop and save that. Let me save that as, yeah, let me save it. Save as P25, 17. Let me just do this here as well. All right, so that is saved. But now what I want to do, I'm going to start new because I want to do a function dy dt. So dy, let me do function here. Because I'm gonna call it when I execute that program. Function dy is equal to the name of the function is dy dt, t and y, and that is dy in this case. I'm going back to this equation here that is given. So dy is equal to what is it? He's given us this k to be minus 0.06, so it's minus 0.06. That's what he's given us, times the square root of y. Square root of y. Okay, and let me do that, and that is done. So that is the function, and just save that. So when you try to save this, it's gonna, again, the function is gonna give you dy dt. You're gonna say yes, don't change that. And I'm gonna go back to 2517 and then call it. And you will see that, well, let me do this here because it should give you, if you do this in here, it should give you t 55.5. Well, it stops at 56, which is that what we want, but we wanted to actually which is 2t here equal t, and let me do, let's press that here, do this one here. So you'll see t equals 56, all right? So if you just do that here, t will give you 56. So it takes 56 minutes to drain the tank. So what I did, I just used the while loop because it makes sense. Just right before it gets negative, which is less than 0, which is in real life doesn't happen. When the tank reaches level 0, that is when it's drained. So right when it does go from reach 0, and you want to stop and you want to calculate the time, and that's exactly what we did. Okay, so you can actually, if you do not want to do the function, you don't want to call that function, you can actually do the function handle right there and do the same thing like I did in the previous example. But it's good to diversify and know that you can always save functions, and you'll be able to use all these tools, the MATLAB tools that you have available. There's more problems that you can solve. Giving you also some homework problem that you have to solve something like that. You can use that's fine. We can use mine to solve problems, or we can do your own. Just be creative. When you're dealing with Euler, RK2, RK4, and Heun methods. Again, I simplify mine. There's in your book and other books, there's more, even MATLAB, like if you see the codes for MATLAB, RK4 and others, a little bit more complicated. Mine is straightforward, and it's just do basic stuff. I try to make my programs as basic as possible so I don't make mistakes. But if you want to spend more time, you can make it more crafty, you can add more things to it, but remember, this is just a problem that we're trying to solve, so we try to use MATLAB but effectively. All right, so I think that should do it for this chapter. Next time we'll let's see what we're gonna cover. Chapter we did 9, we're gonna do chapter 10 next time, and we're gonna do the Simulink. We're gonna start with Simulink, and Simulink is continuation of what we just did, because we're gonna be working with a lot of differential equations, but you will be able to solve these equations that we, the RK4 method, which is a great method that we use ODE 45 for it in MATLAB. It's a great, but also Simulink, when we start solving problems and getting a response for a signal, or a response for an input function, for a transfer function, you'll see how easy it is to use Simulink. So spend some time also as well. Most of you will use Simulink in control systems, those for mostly mechanical engineering, and we use Simulink extensively to calculate response for all types of engineering systems. So we'll talk about it more next time. Thank you very much, and we'll see you in the next lecture.